Hi, with Team 7, we are going to introduce the thesis, Intrinsic Image Transformation with Scale Space Decomposition. This paper was published by Le Changcheng, Chen Yizhang, and Zicheng Liao in CVFX 2018. They propose a new network structure for decomposing an image into its intrinsic albedo and shading. They evaluate the network on MPI's Intel dataset and MIT Intrinsic Image dataset, and delivers a clear progression over state-of-the-art. There has been an emerging trend in representation learning. That's to say, it learns to disentangle from an image the Latin code accounting for various dimensions of the input. For example, illumination, pose, or attributes. The contribution of this work is in developing a scale-space decomposition network for intrinsic image generation. They do this by reviewing the classical Gaussian and Laplacian pyramid structure with learnable down-up samplers. The result is a multi-branch network that produces a level of detailed decomposition of the output albedo and shading, and the decomposition components are implemented as subnetwork, which in turn are collapsed to fit the target image. In this figure, as we can see, given an input image, the network jointly produces Laplacian pyramid components, and the component collapse into the target albedo and shading image in high quality. The network features by multi-channel architecture, and it treats intrinsic image composition as image-to-image transformation in separate frequency bands in the scale space. A series of solutions have been seen since Barrow and Tannenbaum first proposed this problem. For example, the retinous metal. With advent of deep neural network, the solution to this problem has shifted to a pure data-driven, end-to-end training with various forms of feed-forward convolutional neural network. Reference 37. The direct intrinsic is a successful early example of this type, using a multi-layer CNN architecture to transform an image directly into shading and albedo. The investigation of image scale space is no less old-fashioned than that of the intrinsic image decomposition in vision. In the 1980s, Bird and Edison proposed a Laplacian pyramid structure that decomposed an image into a hierarchical level of detailed representation using successive Gaussian filtering and a DOG operator. The convolutional network provides a natural hierarchical feature pyramid for multi-scale information processing. The work of Lai in reference 28 utilizes a similarly deeply stacked network and feature maps to generate image detail map of multi-scale for image super-resolution. Notably, the work utilized hierarchical features from a CNN network for multi-scale processing. Also, there is a variety of vision tests that can be formulated as image-to-image transformation problem. Intrinsic image decomposition is one such example. In reference 23, Isola introduced an image-to-image translation network for several other tasks, including image colocalization, sketch-to-image, and image-to-map generation. In this work, they model the image-to-image transformation as a conditional generating process and use an adversary loss for network training. A set of other vision tests, such as dense pixel labeling, for example, object segmentation, and depth estimation from single image, can also be framed as the image-to-image transformation problem. That is, to map pixel to pixel, instead of hand engineering the mapping process for each test individually. This paper engineered a generic extensible network architecture. Features in exploiting the dimension of scale space decomposition for the form of input or output transformation.
Hello everyone. We are now going to look at the proposed method for this intrinsic image transformation. So first let us see the outline of the method. Here first we are gonna create a network structure for decomposing an image into albedo and shading. and then expanding our output images into their Laplacian pyramid components, and then develop a multi-channel architecture to learn image-to-image transformation in successive frequency. So here, first let us consider the transformation of an input image to an output image, where it is highly nonlinear and pixel-wise non-local mapping functions I to Fi. So deep convolutional neural network is considered to be one of the general network for many many of this kind mapping relations. So in this we are gonna adapt the network architecture for image to image transformation, where both the input and output are images and have a natural level of detailed pyramid structure. And hence the mapping functions linking to the input and the output also have a multi-channel decomposition pyramid hierarchy. So let us look at the background that is required for this method, and we write the Gaussian pyramid of an image as I naught I1 to Ik, where I naught is equal to I and k is the total number of layers, and the kth Laplacian pyramid layer is represented by this equation, and then Laplacian pyramid expansion of image I as L0 of I to L1 of I to Ik, where Ik is the lowest resolution defined by Gaussian filter. And let us see the network architecture and reformation. First, let us use a simplified networks of two blocks L and H to model the mapping I to Fi. Here, L refers to the mapping of low frequency band and H refers to the mapping of high frequency band. With the skip connections and summation of the output of L to the output of H is an instantiation of ResNet network. And step 2, by applying Laplacian pyramid expansion, the loss we split the loss of step 1 into 2 into 2 into two components. The output of L is refined to fit the Laplacian detail component separately. The output of L is restrained to fit the low frequency Gaussian component, and that of H to fit the Laplacian detail component separately. This reformed network is equivalent to step 1 but with tighter constraints. A critical transition happens between step 2 and step 3, where we rewire the two stacked blocks into parallel branches by connecting the output of L to that of H with summations and adjusting the loss of H accordingly. Equivalent forms of Laplacian decomposition equation that have residual components moved from LH to RHS with necessary sign changes. So this structure is equivalent to the Laplacian decomposition equation. So this network structure is the building block for our final extended model. Our final extended model looks like this, for which we have introduced multiple sub-network blocks H0 to Hk-1 for the high frequency bands and one block Lk for the low frequency. So this is in analogy to the Laplacian pyramid decomposition structure. The inputs to the network are downsampled in cascade, and outputs of the networks are upsampled and aggregated from left to right from the target output. All of the network blocks share the same architectural topology, which we refer as residual block, which you are going to see in next few seconds. The residual blocks are end-to-end convolutional subnetworks that share the same topology. and transform the input in different scales to the corresponding Laplacian pyramid components. Each residual block consists of 6 concatenated sequences such as a 3 by 3 convolutional filter, and then ELU. ELU is uh, expanded as exponential linear units, and then 3 by 3 convolutional filter, and then one ELU. Since we are predicting per pixel value from an input image, no fully connected layers are used. Specifically, in each substructure, the output of the last convolutional element is element-wise accumulated with a skip connection, and the result is the input of the last ELU unit. The intermediate uh, in this structure, we are gonna add a 1 cross 1 convolutional filter to skip the connection path of the first and the last layer for dimension expansion or reduction to match the output of the residual filter. And this is the block diagram of that. And we use ELU as our activation function. This is because ELU can generate negative activation values where x is less than 0 and has 0 mean activations, both of which improve the robustness to the noise and convergence in training when our network becomes deeper, and it also memory efficient and 2 times faster than BN layer. Next, we are gonna look at the self-augmented training, uh, where a data augmentation strategy for incorporating unlabeled images to self-augment our network training process. The idea is to employ a forward generative model to generate new training pairs for a model by altering parameters produced by the model to be augmented. So here we start with a preliminary network trained with a moderately sized data set that has ground truth albedo and shading, and then apply the network to a set of new image and obtain the estimated albedo and shading, and we can generate a new image from the estimations. So this training method is to give the wide variety possibilities uh, of image, and it also improves the efficiency. So to introduce further alteration, we additionally apply an adaptive manifold filtering, which is shortened as AMF. So this is operated to the extracted albedo and shading layer, and this helps us to synthesize a new data, and then we combine the both data to get a image which differs from the input image, and this helps us to synthesize new data for training more pairs of images. And now let us look at the evaluation, and over to evaluations and experimental results. Thank you.
including the focal and emotion blur, complex lighting, atmosphere effects, and using the data sets and the local occlusion boundaries were selected. You can see the motion boundaries, and the motion boundaries have a flow error which increases as the function of proximity. There are unmasked regions, which these regions can be included in one frame but not in the next frame. And the reason is because of the large motions, these regions get rippled. They fade into each other. And there is a multi-frame hallucination layered images. Yeah, for this data set, they used different levels of realism, and they used a final render which has the constant brightness everywhere except in the occlusion regions.